All right. Good morning. My name is Derek Lay. I work with Percy Smith and Nick Bruno. We're the Busy Bees, and we're looking at chemosensing, which is just a study on morphological effects through robotics. So our project overview is we basically are aiming to develop chemosensory feature to the existing Robogami robots through these following things, which is conducting different morphology study. So we have a honeybee with no rami, a moth with a low density rami, and a moth with a high density rami. And rami are just those small structures on the side of the antenna. We're also going to vary the distance to the odor source, the odor source concentration, and then we're going to compare our results with just that of a blank sensor mounted downstream. And then we're going to categorize all of this as our biological principle of flow capture ratio and leakiness. So what this looks like is we have a uniform odor field. Our odor is concentration of gas or humidity. We're still trying to sort out what the best to resolve is. We think we're aiming to using a gas, but we might have to do something with humidity. And then we have our antenna morphology, our mounted sensor, and then our robot body.
Yeah, so to talk through kind of the structuring of communications and interactions across our robot, we're planning to use the BME 680 sensor, which takes measurements of temperature, pressure, humidity, and VOCs, as well as multiple other types of measurements. And so that's going to be communicating with our Arduino Nano over and using Bluetooth to transmit signal back to our central communications device, which we're going to set up probably either through an app or through a portal on a computer. The robot will also be hooked up to motors as it currently is, and you'll be able to drive that from the Bluetooth central device as well. And then, as you can see, right to the right of our BME 680 sensor is an antenna. This is just representing how the airflow would be passing through the antenna and interacting with it to change how the airflow would approach the sensor as it would without one there. So
Yeah, so our objectives, our main hypothesis that we're going to be testing is that morphology of an insect antennae affect olfactory performance through these things called relevant capture ratios. So we're going to have this sensor mounted downstream of the antenna, like we showed, and then we hope that there will be optimal morphologies for given flow conditions. The novel biological principle, however, is both through leakiness and flow capture ratio. So leakiness is basically just the amount of flow that's going to a surface relative to the incoming flow. And the flow capture ratio is this leakiness normalized by an effective sensing area. So that way it will inform us on our odor capture efficiencies rather than just the amount of flow that's going through an object. So to do this, we looked at a discovered decomposition of a paper titled Leakiness and Flow Capture Ratio of Insect Pectinate Antenna. And this basically takes a biological sensor of a moth, adapts it into a 3D printed part where they vary these rami. So on the right-hand side, you can see all the linkages, and they either add more or less of those. So looking at the background hypothesis, we have basically that leakiness and flow capture ratio affect olfactory performance. Now, they went through and 3D printed, conducted a large experiment, measured all these fluid velocities, normalized them with the effective areas, and found that leakiness and flow captures are functions of rami density and air velocity. However, they didn't introduce actual odor to the system, which is what we aim to do in our work. So looking at the literature review through the analogy check, we have a lot of things that are similar, but some that are different. So for the most part, I'll address the differences and how we'll overcome them. So the main one is structurally, moths have pores on their antenna where we'll be using a sensor. This will be overcoming because we still want it to serve the same purpose. So we're just going to validate that our sensor can detect concentrations of odor. Other ones include the operating environment, which we can recreate indoors by either turning a fan on or changing the orientation of our robot to try to mimic what it would be like in nature. And then the last on this part is the size, which will just validate that we're staying at the same Reynolds number, which is keeping the consistent physics of the flow. So we still should be able to use the relevant theoretical models from the paper. Lastly, on this slide, the one big thing is that MAWs have flexible RAMI, and we are using a stiff 3D printed or maybe laser cut material. So this we'll just overcome by realizing that our material is going to have more drag, which will lead to a higher energetic cost. And we will definitely make note of this. And our big constraint is we're limited to the 3D print resolution. So we're going to overcome that by scaling our part up so we can actually have a similar geometry.
All right. So for the experimental methods, we'll obviously start off first with varying constructions of antenna. This would be varied on either Rami density and possibly the angle. With the downstream sensor, we'd be able to detect different flow levels based off of time and density from the varying antenna shapes. The testing overall will include an odor source in which we can vary the robot distance and placement from it. We'll have a constant advective transport, which would be just a basic fan, and our odor source concentration will also likely vary with distance. What we kind of hope to get from these results is categorize our sensor based on flow capture ratio, source concentration, and flow velocity. The overall testing protocol is mainly going to be based off of calibrations of sensors and antennas, making sure that they're specifically integrating with our mounts, and we're looking for any possible error within the sensors themselves, and also double checking that personal equipment and sensors are approved and ready to be used on our robot. The main failure protocol is going to be just backups for each component, whether these be different kinds of sensors or a secondary same sensor as well, different antennas versus like what material, if they're 3D printed, laser cutted, or and so on. And then extra body structures that we might need as well, because we should likely be iterating each design on each attempt. What we hope to kind of validate our hypothesis is that from these measurements, we'll basically be able to determine odor flux and cross-reference the antenna morphology, which would allow us to see variation in the signal when exposed to the same pollutant conditions. Our anticipated results will that the robot should be able to smell and have olfactory decision-making processes later down the line. The robot should be able to detect concentrations from 0 to 5 ppm TVOC at distances of hopefully 2 meters away, and each antenna morphology would likely show a different flow capture related to the Rami density.
So going into some of the alternative options for our project, we were thinking about swarming as one of the options, in which we would have multiple bots that could also, sense to be able to get more of a kind of network of measurements to kind of like increase the resolution of a plume of odor. Additionally, we had considered the orientation of the antenna, as you can see in this diagram on the right, just kind of changing how exactly we have the antenna angled to see if there's an optimal position in which we would have better sensing ability. Going into performance metrics, the sensor will have flow capture ratios on the same order as in paper 1, and adding an antenna upstream of the sensor would increase the performance of the given sensor, because the sensor is going to act as a paddle, and the antenna will force leakiness and transport flow to the sensor surface effectively, allowing for us to see more effective flow capture. Talking about the significance of the project, knowing which antenna orientation and shape works most effectively when we're sensing a specific odor would allow for us to develop more efficient sensing robots that could be used in small, hostile, extreme, or commercial environments. There's a lot of different applications for this sort of tech. Additionally, sensors are currently just kind of interacting directly with the environment without enhancement. So this would allow us to build a coupled system and define criteria for such a system that would enhance the odor capture, and thus would improve the scope of and relevance of the actual tech itself. And it would increase the application range for low cost sensors and air quality emissions testing.
And here are just our references, and we thank you for your time.